Hi, Dan. Welcome to Concentrating on Chromatography. I appreciate you joining me today. If possible, could you provide a general introduction to your work?
Kind of the tagline is bringing mass spectrometry to life, and the focus of it is dried matrix spots. So that's the target application. So how do you automate mass spec? How do you simplify the sample prep process? In dried matrix spots, it can be blood, urine, saliva for biofluids, or it could just be really any liquid sample dried down on paper. And how do you get meaningful information back out of it?
I thought it was really cool that you were able to provide a pretty creative metaphor about giving the mass spec sight through the computer and taste through the surface sampling. Could you walk the listeners through what that concept really means?
Clever. Appreciate the little pat on the back there. I kind of felt like a bit of a Dr. Frankenstein making that analogy in the sense of, the mass spec's the stationary instrument that sits on top of the bench. And so as you try to automate that, both the sampling process and then the mass spec analysis, how do you do that? So first off, the mass spec needs to be able to see. So I had this idea. My background's mostly microfluidics, but if you could impart into the sample some sort of pattern, that if you could give the mass spec quote unquote eyes, so to say, and that's where a camera comes in. So we have a sort of an automated sampling platform where it can move the sampling apparatus around, but it's almost operating blindly, or it's only going where we tell it to go. So now if you can give it sight through this camera computer vision program, and it can recognize a specific pattern on your substrate, it can essentially steer itself towards where it needs to go. And then the taste aspect was sort of the analogy for like, how do you actually get the sample into the mass spectrometer? I think everybody's probably familiar with direct injection, like you might see with GC or some sort of LC method. In this case, it's a unique sort of sampling tool called the Liquid Microjunction Surface Sampling Probe. Bit of a mouthful, LMJ-SSP. But it's essentially just a continuously flowing droplet on a stick, two concentric tubes. And so you just touch that to the surface. That probe is held by the printer, which is guided by the camera. It's letting the mass spec lick, we kind of say, just as an easy way to phrase it, your sample, and you get direct surface information from that.
You mentioned a 28-fold reduction in CO2 and a 21-fold reduction in organic solvents. Was there a specific moment or bottleneck that made you realize or want to focus on greener chemistry and sustainability in terms of this work?
I appreciate that question. So I previously would have just called myself an analytical chemist and left it at that. And I really didn't think of things beyond the sort of minutia of what's the standard deviation, what's the reproducibility of the method. But I learned about systems thinking as sort of how do we think about more broadly the impacts of our work and what are we striving towards. I had gone to an IUPAC conference in the Netherlands, and I met David Leviska, who's the one of the program managers with the ACS's Green Chemistry Institute. And just a really casual conversation we had kind of introduced me to green chemistry isn't just for the synthetic chemists. It's really for all chemical practitioners. And so talking about those reductions, those are derived from using these dried matrix spots as an alternative to maybe direct blood sampling, maybe traditional methods. If we can bolster this dried matrix approach, there are significant environmental impacts. You can get around cold chain storage, reduce solvent consumption, especially with this LMJ-SSP technique. I did the green chemistry summer school offered by the ACS. I've been to a couple green chemistry conferences, got a poster award at one. I mean, really, once you start seeing how your work, there's always ways you can do things greener. And that's in the sense of cost effectiveness, time effectiveness, waste hazard reductions. And so, yeah, when I kind of just stopped thinking about myself and zoomed out to more broadly what impacts am I having, it totally changed the way that I approach my research.
Yeah, quick shout out to My Green Lab. I'm not sure if you're
Yep.
familiar with those guys, but as someone who works for a manufacturer, what they're trying to standardize on the manufacturing side in terms of the labeling of products, in terms of their sustainability, I think over time is going to be a real game changer for the lab industry and hopefully on par with what's become expected of home appliances with the Energy Star stickers, but with actual information in terms of their labeling and the various categories. I'm pretty excited for that to take off and for consumers in the lab to be have the information sir, to really make more educated decisions on the sustainability of the available products.
I mean, the labs are able to get these, because I think My Green Labs does like a certification or some sort of. Yeah, I mean, I think it's awesome that people and chemists in particular are starting to. I mean, I know in analytical, there's now different metrics for assessing the greenness of a particular method, whether that's just some sort of extraction step or even maybe the chromatographic workflow. And I mean, that goes all the way from just, are you using a hot plate or solvent toxicity? So yeah, I think the more information that's available to people, as well as the alternatives, right? Is it, I mean, there's always pluses and minuses to things, but at least having the information accessible and digestible, I think that's a huge benefit to the field.
I totally agree. While we're on the sustainability topic, it might make sense to jump ahead. You had mentioned shipping some samples without dry ice, and I know that's an area where lab managers could spend a fortune on shipping biological samples. How close are some of those alternatives to being viable?
The whole cool, and that was something too, just I had been working with this idea of dried matrix spots. They've been around clinically for quite some time, but they haven't really seen some new improvements. And especially when you look at them in the context of greenness, you can mail them through standard postal services. Whereas if you were trying to transport a blood sample or some sort of biological fluid, generally you're going to need the cold chain transport, which is where that big reduction, that's an estimate. But again, just for some sort of contextualization, it's huge CO2 emissions just associated with that. I mean, there's several commercial microsampling solutions available for especially blood. That's a really hot one, just because that's such an indicator of health. You're looking at biomarkers. I think there's even free DNA that kind of floats that can sometimes indicate cancer, metals, or whatever you're really looking for in blood. But lots of microsampling technologies. It's going to take a bit more time to, again, it's hard to compete with LCMS just given how long it's been around. But that's not to say that you can't come up with alternatives. And I think that's where this microsampling, the dry matrix spot field is trending towards is, there probably will be instances where you won't fully ever eliminate LCMS, and I don't think you'd want to. But there's areas where it can be complemented if you're saving, again, on having those, especially for rural areas, or if there's some sort of centralized testing lab that you can just mail these samples into versus having to deploy people into the field, which then that's a whole nother thing of, it's not even the chemistry you're doing, but if you're having to like take a flight or drive somewhere, I mean, that process itself is creating emissions and all sorts of things. And there's just so many interconnections that systems thinking. My work in particular, still very early stage. I presented it at a couple conferences. I'm hoping to get a publication out. I really took a fundamental look at, okay, this LMJ-SSP technique is good. It has elements of chemical greenness, but a critical part is the substrate. I mean, that's what a dried matrix spot is, right? You've spotted liquid onto oftentimes filter paper. But if we can improve the substrate, just really the foundational premise of these dry spots, that's going to have implications for having better analyses, better commercial viability. So that's where a lot of my research has been lately, is sort of the microfluidics and the micropatterning of the preparative substrate.
Your work relies on surface energy traps to confine the liquid droplets, and this wasn't something I was too familiar with before now. For the chromatographers listening who are used to working with vials or maybe the 96 well plates, can you explain what an SET is just in general, and how do you use lasers to trap a liquid on a flat surface?
So you can think of a surface energy trap, or we call it an SET for short, as like a very small well. I think that's a great analogy. Um, and so how they're prepared, where the laser comes into this, is I'm using paper. I coat that paper with a surface coating that's hydrophobic. So you've got an entirely hydrophobic piece of paper. You stick it under the faucet, it won't get wet. It's kind of fun to see. Then you come in with a light laser and just create a circular pattern. And that laser ablates away just enough of the surface coating that the paper's re-exposed in the shape of a circle. And so that right there will trap liquid if you just deposit a droplet onto it. And then, of course, we all know a droplet will dry down. And so it just dries down specifically in that little half a millimeter circle. You've essentially trapped what was a 1 microliter, 2 microliter droplet, has now been dried down and in effect pre-concentrated. There's a little bit of nuances there, but I think it's simple to say that you've pre-concentrated it and definitely end it down in an area. And it's cool too, like when you put something in a well, you don't have to worry about it spilling out the bottom of the well, or I guess if you put too much, it'll overflow. This paper that's been modified and laser patterned, you don't have it diffusing outside of the circular boundaries in a lateral direction, and you don't have it diffusing deeper into the paper. It really just dries down perfectly on top in the little well that you've created.
A critical part of the workflow is the drying down phase, which makes a whole lot of sense considering a dried matrix spot, DMS. And obviously, there's a tie in there with my work where at Organimation, we're coming in after the extraction step and doing the sample concentration or the sample drying, typically ahead of GCMS or LCMS. Does the uniformity of that drying process affect the results? And do you see a difference in signal intensity based on how fast or how slow the spot dries?
Yeah. Backing out a little bit, that was also one of the impetuses for this project. For people who maybe don't know, like when you prepare a dried matrix spot, a very common example is like when newborns get the heel prick. It's really just putting a drop of liquid onto regular filter paper. And just like a napkin, or you spill something, you see it just diffuses kind of, I'd say, randomly, or at least without any sort of control. And when you look at the pictures, and this has been known for some time, of like how blood, it's the coffee ring effect, right? Like as it dries out, analytes will diffuse non-uniformly. And when they do these dry matrix spots, they just literally like a hole punch. They'll punch a hole out, and then that gets digested. So it's a comprehensive digestion to then do LCMS, MS. But where you punch that hole could have an effect on the concentration of your analyte, how it diffused within the paper substrate. And those circles can be on the order of several millimeters. So, I mean, there's a lot of, I'd say, irreproducibility in where that hole gets punched. You could punch enough holes, and I guess you could have an average, but still, I think you get the point. So then with these SETs, I can create those on the order of the size I'm using now is about 0.5 millimeters, 500 microns. That's a lot less surface area for something to diffuse outwardly. In addition, that diameter is smaller than the diameter of the probe with which it's being sampled. So you're getting a comprehensive sampling. It's not exhaustive, but it's at least differences in diffusion have been significantly minimized. I've tried to map out using SEM to see like, okay, can I actually discern that, this analyte's a little more concentrated in this area just using like a zinc chloride solution. From what I can tell, it's really quite uniform. You got to be careful not to generalize too much of, how are the organic analytes performing versus inorganic analyte in aqueous solution, but it's promising. And I at least am confident that this approach that I'm doing with laser micromachined SETs helps to combat that diffusion problem that's in traditional dried matrix spot. And then the other question, which I honestly, I wasn't aware that that was a problem in sample prep, is the rate of dry down. So that's not something I've studied, but I think that's an interesting question to look at and how you would go about interrogating that.
Totally. And it's a different space for sure, but in terms of the approach that organimation applies, one of the advantages to nitrogen blowdown is supposed to be that it's a gentle process where it can be a much better fit for certain samples compared to like a centrifugal evaporation, such as a speed vac, where you're really subjecting the samples to that motion while under vacuum and completing the evaporation process in that way. I believe you already answered most of this question, but in case you had any follow up notes, how does your method using specifically the hydrophobic coatings and the laser patterning solve some of the general headaches associated with traditional paper sampling?
Yeah, certainly when you try to go down to the smaller diameter traps, you're looking at wax printing. You can't really get the precision of the laser, which comes with a trade off. The laser is a costly tool, which I think that is a factor of greenness, right? How accessible is this? There's definitely some scale up considerations if this was going to end towards commercialization. If you're going to ambiently sample these paper substrates, you want that analyte dried down to be as superficially on the substrate as possible, especially for our probe. Because when you're doing the digestion, it really doesn't matter how deeply it goes into the paper, how superficially it goes, because it's all getting digested in the vial. You're using the extract and injecting that into the mass spec. But in this case, with this droplet on a stick, the LMJ-SSP, if your analyte diffuses outwardly and deeply into your paper, already you're going to face signal reductions. What's taken me probably about a year and a half to refine this paper to a point where it's good for sampling. I won't say I've got it perfect yet, but it's better than it was. It's still challenging because it's a liquid solid extraction in a sense, right? The analyte is dried down into the paper. You've got this microliter volume droplet on this probe that's trying to remove the analyte that's adhered, bonded to the paper substrate. Versus if you've got, again, the traditional digestion with some sonication, a little bit of acid, it would be much easier to loosen it up and then get it on the LC versus this way. But the advantage of this hydrophobic coating, it's super cheap. And if it's from a ethically managed, sustainable forest, then the paper itself is a sustainable substrate. So now we've got it in a way where there's no, and if you kind of compare to on the analytical side of things, I don't think any mass spec technique is easy. It's always some level of training. But I will say that with this approach, if we're able to circumvent chromatography, setting up an LC method, that, we're using just really one same mass spec method, press play, the probe goes, touches, and then on the triple quad, you get the output fairly quickly. I think that's an improvement overall to the workflow, especially when it's functioning perfectly, to be able to just slide this dried matrix spot onto the sampling stage, the camera recognizes the pattern that flanks the SET. So it's like crosshairs almost. The camera targets the crosshairs, triggers the downward motion for a set dwell time, get enough signal, and then voila, you've got sampling. I think on both the sample prep end and the analytical side of things, this hydrophobic coating paired with laser micromachining, paired with mass spec, it does bring some benefits to the field.
When preparing for the interview, I had noted that you were recently named a 2025 CAS Future Leader, which is a huge honor from what I understand, that it's the top 35 early career scientists globally. So I'd love to hear what that experience was like and how it shaped your view on where the analytical chemistry field is heading.
Yeah, that was a huge honor. That's how I came to be at ACS Fall, or how we got to chatting. But yeah, I was really privileged to be a part of this year's cohort, CAS Future Leaders. I mean, it revealed to me a couple of things. First off, that there's a lot more that goes into being a chemist than just, I think, good research. There's also the whole community side of things. In terms of the analytical field, I mean, being there evidenced that if you're not working cross-disciplinarily, cross-culturally, you're missing out on a lot of things. You're missing out on people who have resources, who are very willing to help you. You're missing out on the perspectives that they bring, the problems of which they're aware that you might not be. So it really kind of bolstered my sense of communicating with people that, okay, these are organic chemists, let's talk, because they may have pain points that my research might be able to see differently, and vice versa. And so also, science communication is something I've been aware of. I mean, I think it's a bit of a buzzword sometimes, but really just the importance of that. And there's skills you can learn. We spent that week in Columbus. We had Jen Heemstra come in, talk about lab leadership. And we had some folks come in and teach us specifically about SciComm, strategies you can use. So really just being a well-rounded chemist and a well-rounded person was sort of the takeaway from that. It was just a fantastic experience.
Yeah, I'll say it's a wide spectrum. I think there's certainly the people that keep their head down and never come to some of the conferences I'm at, whether it's ACS or ASMS. And then there's the people who are pretty consistent presenters at these events. And then there's also some people who I feel have gone above and beyond in the online space, where they might regularly update their website that's devoted to the lab that they're doing and really pushing out their published work, not just being in the journals, but actually going above and beyond with the sharing aspect, and even coming on podcasts like this one to talk about their work. I appreciate the initiative from the people who are out there sharing all of their work, because that's the main way that people outside of the lab can learn and educate themselves on the latest and greatest, I suppose.
It's true. I think another point that came up was also just advocating both in the community level as well as for policy. I think it's all well and good if we kind of talk with each other, but we've also got to get a little outside of maybe our comfort zones or just our boundaries that we normally operate in, whether that's the boundaries of academia, the boundaries of our particular industry, and just talk with people about the science that we're doing. Also, science is oftentimes very publicly funded. So I think it's a really good way to share. This is the impact that we're trying to make with the support that we're fortunate to receive from people, from communities, really. And I think just when you have scientists talking with their communities, and it's also two-way communication, right? You practice, okay, where am I sort of maybe not communicating clearly enough? Maybe kind of over complicating things. I think you learn too of like problems just that the community might have in terms of sort of wastewater challenges. You also, when you connect like local industry with academia, it really just opens up whole new possibilities of research partnerships or outreach partnerships, and communication's a key part of everything.
Yeah, I think you made a couple excellent points there, but especially NIH as an example. I could see in the US, somebody reading a news article and looking at the budget for NIH and not even being able to wrap their head around that amount of money. But part of the reason it's so challenging to understand how that money is spent and why it's critical is because they can't really connect it to the science and the progress that's being made on all these real issues, whether it's environmental or health related in terms of the critical research we need. I feel like it's easy from where I sit, but I could see how people outside of anything connected to science could have a really hard time connecting that public funding with solutions and progress that everyday people really care about.
Yeah, it takes a lot of time too. I mean, one thing when I have a little more time, I'd like to be more intentional to support them. But I love I've seen some companies, or I don't know if universities sponsor them, but it'll be like a pub night where it's like a science chat or something, and just bringing in different people talking about something, whether it's the science that they do or some sort of just science themed talk. I think those are great outreach events. If people are interested, they can show up and conversations can start. Yeah, I think outreach is a huge part of transparency.
Totally. One thing I'd love for you to get into is some of the 3D printer work that was involved. For any of the DIYers we have out there, the tinkers, I'd be very interested to hear about some of the, not sure if the right term is jailbreaking, that may have been done to incorporate the 3D printer work with the mass spec auto slam for. So anything you'd like to talk about there, I think is super interesting.
Yeah, and I think that element of the work represents something I kind of mentioned earlier of the importance of cross disciplinary collaboration. So that 3D printer element, because XYZ controllers have been around for some time. You can mount anything to an XYZ controller, manipulate it to your heart's content, but they're costly. And so our lab, several years ago, was looking, how can we exert XYZ control over the probe, but how maybe can we do that in a more cost effective way than buying something that's several thousand, $10,000? Herman from the group started that sort of, let's call it customization of the 3D printer, writing this kind of from scratch homemade program where you could input the code to the printer and say, move 20, right 30, downs, whatever you needed to do. And it worked. But again, that was sort of a chemist coming at this in a DIY sense. I mean, a very technically savvy fellow. But then we sort of had the luxury of being able to partner with a group from computer engineering to then say, here's the base. We want to improve it. And so through that partnership, they were able to bring a lot of both on the sort of user interface side and also on the back end of this program, where now it really is quite simple to just sort of input your coordinates. You can control the dwell time. I mean, the idea kind of came out of our chemistry centric group, but then it was really bolstered by partnering with people who specialize in coding and that creation side of things. Now it's at a point where it's interesting to see how it's evolved as well. Because then when I came in, I saw that, hey, there's maybe a way that we could incorporate computer vision into this, giving the sight to the mass spectrometer. It's like, yeah, that's a great idea. I had the idea, but I didn't have the technical know-how of, okay, well, there's machine learning, there's object detection that goes into computer vision. But again, through having that relationship with computer scientists, we're now able to add in this vision element to our sort of in-house computer program that allows us to touch control with this 3D printer setup. So it's a pretty cool DIY example from the lab.
Absolutely. Yeah, and it's something we're obviously seeing a lot in manufacturing in terms of not necessarily the actual machine or production quality parts, although that's really the long term goal. My favorite example is always the auto mechanic that doesn't need to send somebody to Napa or some other store. They could just print the part you need and install it that day. Or certainly, there's a lot in our space being done right now in terms of just physical prototyping for sizing, and it's real exciting. And I'm sure it'll change a whole lot, especially with all software with AI over the next 2 years. Being able to use a lot of those tools will be a lot more user friendly, I think.
Yes. And I mean, just one kind of follow up to, I mean, the 3D printer, I think that example is a very unique one because when you think of 3D printing, you don't think of using the infrastructure to do something. You think of the thing that gets printed, the part, the component. Whereas in that case, we're using literally the 3D printer itself. We've kind of retrofitted it. But I mean, there's several of my research projects. Had it not been for just the 3D printer capabilities, I need to print this specific piece, sort of made a micro droplet generation device that was the holder of it was using an entirely 3D printed component. So yeah, just the possibilities that are afforded by, and I mean, they're really not, terribly expensive too, right? I mean, the cost of it comes down every year just for a very functional model. So yeah, having one of those, several of those in the lab is a huge advantage.
I couldn't agree more. Well, Dan, this has been great. I really appreciate you sharing your work with the audience, and certainly congratulations on what was a great 2025 for you with the award. And I look forward to seeing you in 2026, hopefully at a conference down the line.
Yeah, I'll be at ACS 150, so I hope I see you there in Atlanta.
All right, absolutely. I'll see you in March. Thanks,
Stay.
Dan.